Thank you again, Professor Baskaran, for your wonderful talk. And for the last plenary speaker for this afternoon, may I call on Dr. Jason Cosme of National Institute of Physics to introduce our next plenary speaker.
Hi everyone, can you hear me? Hello?
Yes, we can hear you.
Okay, good.
Hello,
That's
sir.
awesome. Yeah, so thank you for having me. It's an honor to introduce our next speaker, Dr. Dominik Šafránek. So Dominik did his PhD in the UK and Austria, working in quantum metrology, which is science about quantum measurements. He derived several now well-known formulas for the optimal estimation of quantum states. Then Dominik did his PhD. He moved to the USA for a postdoctoral position, going into a more fundamental field, realizing that there is no good definition of entropy that would express the second thermodynamic law in quantum physics. So together with Anthony Aguirre and Josh Deutsch, he developed the framework of observational entropy, which is something that I think he will discuss today. He continues to develop this framework to this day, now as an independent researcher at the Institute of Basic Science in South Korea. So let's all give a warm welcome to Dominik. Dominik, please take it away.
Thank you for your nice introduction. Let me just share the screen. Okay. Can you hear me okay and see this okay?
Yep.
Awesome. Okay, so I'm going to present this talk about observational entropy, which I call which entropy increases in isolated quantum systems. We start with a quote from British astronomer Arthur Eddington, who said that if your theory is found to be against the second law of thermodynamics, I give you no hope. There is nothing for it but to collapse in deepest humiliation. So these are strong words from a British astronomer. So let us revisit the second law. It states briefly that the entropy of an isolated system cannot decrease and is constant if and only if all processes are reversible. But there's this this is a different statement of this law, but just reworded. But there is a different part of this law which defines entropy, because here the entropy is not really defined, right? So we say entropy increases. So the statement is that there exists for every thermodynamic system in equilibrium an extensive scalar property called the entropy. And if I just highlight, oh, I don't know what this one. That's the pointer. So you see this in equilibrium. That's the point, right? So that's a problem. Why is it a problem? Because the law states that such a quantity exists for systems in equilibrium. And at the same time, the law states that entropy of isolated systems left to spontaneous evolution cannot decrease. So it increases. But that talks about composite systems, which are not in equilibrium. Let me illustrate on an example how it works. So the question is how to define entropy of a composite system, which has parts that are not in equilibrium with itself, so that this entropy that we are going to define increases in this system. So with that example, how it works in classical physics coming from Boltzmann. Let's consider this example of two boxes interacting. This system A is in equilibrium with itself, system B is in equilibrium with itself, and they just start to interact. So in the beginning, the second thermodynamic law states that there is some quantity called entropy, this entropy of A, entropy of B, and we say, well, it's probably additive, we just add it, and that's our entropy of the full system. And then when we remove this partition and the particles start to mix and interact, the system reaches thermal equilibrium. And then in this stage 4, again, the second thermodynamic law guarantees that there is a quantity. And that quantity gives you some different number, right? And the different number is basically associated to any stage 2, 3, and 4. It depends it's because it depends only on the variables, macroscopic variables and boundary conditions, which are all the same on all these instances. So actually the thermodynamic entropy has this jump from one value to another. But really, it's really defined only in equilibrium here and only equilibrium here. So we would like to define some entropy that can also work outside of equilibrium. But why do we want to do that? Why do you want to define such entropy? Because we want to talk about entropy increasing with regards to second thermodynamic law without having to refer to the equilibrium state that is achieved along time limit. As an example, people say entropy of the universe increases. But this is kind of an empty statement, right? Because if you don't have a definition of entropy out of equilibrium, what you would need to talk about is really entropy when the system equilibrates. But equilibrating universe means that the universe reaches thermodynamic death, which is going to happen in maybe 16 billion years. And that's not very useful concept of defining entropy of today's universe. So what do people mean when they say this, like entropy of the universe increases? It cannot be thermal entropy because that is not defined there. What is meant by entropy here? What is this thing that increases? So the question is, what entropy increases in an isolated system? Let me go to another quote. So when Shannon invented this entropy in 1948, he didn't know how to call it, and von Neumann told him you should call it entropy because it used to be used before in statistical mechanics, and especially because nobody knows what entropy really is. So in a debate, you will always have the advantage. Back to our question. So which entropy? Obviously, nobody will know what it is, and there are, of course, many entropies. So this is the entropy zoo. I don't want to overwhelm you, although maybe I'm doing it right now on purpose. But basically, there are three groups of these entropies: coarse-grained-based entropies, thermodynamic, and information entropies. And these could be differential, classical, and quantum. This is not the full list, but kind of the more famous ones. And I'll talk a bit about these three. There is one common denominator for every entropy, and that its increase signifies some loss of information, and different entropies signify loss of different types of information. Closest entropy is the one that was introduced in 1865, and it's related to change in the heat in the system. This is exactly the entropy that's defined in equilibrium. Thus, it's not the generalization that we are looking for. And its increase signifies loss of information about energy microstate that the system is in. That's simply because if you add heat to the system, you increase its energy, and then there are more microstates the macroscale could correspond to. Then the von Neumann entropy introduced by John von Neumann in 1927, you probably know this formula. It looks a little bit like Shannon entropy, but there is a quantum state here. So this is the density matrix. You take trace and trace of the row log row. And this entropy was actually criticized by von Neumann himself in 1929. He said that this expression of entropy, which was not called von Neumann at the time, is not applicable here in the way they were intended, as they were computed from the perspective of an observer who can carry out all measurements that are possible in principle, regardless whether they are macroscopic. And he even wrote this exclamation mark here that every rheostat has entropy 0. This is a problem because this is not a good property if you want to define thermal entropy for some state, and all rheostats have entropy 0. That's just not a good definition. And secondly, it stays constant in an isolated system, so it cannot generalize second thermal law because it's always constant. Fundamental entropy of the universe is just constant. And this signifies loss of information what the microstate is if this entropy increases, because it changes the density matrix. So finally, let me get to the main topic of this presentation, and that's this observational entropy. There's been some quite evolution. It's really a generalization of Boltzmann entropy since 1987. Then coarse-grained entropy introduced by actually von Neumann as well in 1929, and then his book 1932, and then further developed by myself, my collaborators, 2019. So Boltzmann entropy for general coarse graining, if you have a microstate xp, which is some position and momenta, is defined in the following way. We associate the logarithm of the volume of the macrostate that this microstate is in. So if you consider this phase space, there's some microstate here, and some boxes that are macrostate, and size of the box is basically this V. So as you can see that if the particle travels during the evolution through the phase space, it just evolves into a bigger macrostate. And that's what we call thermalization. And this entropy increases in an isolated system. But okay, let's talk about what it signifies. So it increases, then it signifies loss of information about the microstate due to inability of distinguishing between two microstates by performing macroscopic measurement. So there's some loss of perceived order that depends on an observer. And this is the example. So if I look at this picture, they look different. And these look the same, even though they are very different, but they look the same. Why is that? Because in my perceived order, these two things can be easily distinguished by some macroscopic measurement, while these things, I have no clue. So these belong into the same macrostate. So entropy associated to these two will be bigger and smaller to these two. So that's an interesting feature. It actually depends on observer's choice. If you want to generalize this to quantum physics or even classical physics, but maybe not with just the point in phase space, but phase space densities, you're going to do something new. So if you have some system where you are not exactly sure about the initial conditions, so you have some phase space density, then you can overlap between many different macrostates. And then you can see it evolves and it still overlaps among the different macrostates. So the definition needs to change. This causes entropy that's basically including these overlaps. And observation entropy is including, in addition to that, multiple coarse gainings and even generalized coarse gains, such as POVMs. And this is the definition. So basically on the right-hand side, you have the mean value of Boltzmann entropy. So this is Boltzmann entropy, that's the mean value. And on this side, you have the uncertainty about into which macrostate the system belongs to. And this PI, that's the probability of the system being in a macrostate. So that's basically overlap of this part here. So that's one probability, and this part here corresponds to the second probability. And for interested people, these are the definitions. So you can see that it's basically probability of measuring some set of outcomes. You can generalize it to POVMs. I can talk about more if some people are interested. The key thing here is that these are general coarse gainings, but not all coarse gainings are created equal. Some are special. And what are these special coarse gainings? There are three of them. One is energy coarse gain. And why is energy coarse gain special? Because energy is conserved in an isolated system, and energy coarse gaining connects this entropy to thermodynamics. Then particle coarse gaining, again, because number of particles typically conserved in an isolated system, or at least its mean, it's kept constant in grand canonical ensemble. And position coarse gaining, and that's because we tend to coarse gain everything in position because physical laws are local. There is some finite speed of interactions and evolution of quantum systems. So locally, we can see the values of any variables spreading in physical space, but not let's say in momentum or energy. It's not local in momentum or energy, but it's local in position. So these are the three ingredients that we are going to use. So we define non-equilibrium entropy as this observational entropy, where you have this system of the system A and system B. So you coarse gain the system A, with energy, system B with energy, and then you take a second corresponding with particle numbers, system A and a system B. And you can see this tensor product here that signifies locality, because this refers to system on the left, this A system, and system on the B as the right system. So this is the position part of it. And as you can see, we did some simulations, both classical and quantum. So these are just two examples. This is the thermodynamic entropy for the initial state and the final state. And this is the evolution of this quantity. So this is classical system. These are a real snapshot of the evolution, and the same for a quantum system, which was simulated on 1D Hubbard model. So that's it. As a conclusion, second thermodynamic law states that entropy increases. Entropy in this law, however, is defined only for systems in equilibrium. So we want to find notion of entropy that is defined out of equilibrium, which gives meaning to this entropy of the universe in increasing. And observational entropy, which is a generalization of Boltzmann entropy to quantum system, is exactly that we were looking for. Thank you for your attention, and this is my email. Please feel free to contact me. These are the two papers that, if you'd like to know more, these are the first two that you should check. And I think to my collaborators, Anthony, Josh, Joe, Dana, and in Korea, Juzar and Dario. Thank you very much.
Thank you, Dominik, for the very inspiring, very wonderful presentation. Do we have any questions for Dominik? If you have any, please type them in our chat panel, or maybe, I'm not sure if you could actually unmute yourself here, but if you could, maybe you could do that as well. Okay, so we have one here from Dr. Kwansing. So is the non-equilibrium entropy you're using extensive?
Oh, that's an excellent question. So it is in some situations and it's not in others. So if you start with isolated systems that have not been in contact with each other, so you have system A, system B, they have not been in contact, so they are not correlated, then it's additive and therefore also extensive. And if you take a long time limit, then it's also extensive and additive. In between, it's not, and that's simply because quantum systems, but even classical systems, are becoming more and more correlated as they interact. These correlations somehow vanish in the long time limit, but in the meantime, it's not extensive and it's not additive either. But we shouldn't even expect that.
Okay, and there's another question from Lemuel John Sese. So from the Poincaré recurrence theorem, the state of a system will return very close to its initial state for a finite amount of time. Now my question, how do we reconcile the definition of entropy to the recurrence theorem?
Oh, well, this is the very same issue that happens also with Boltzmann entropy and classical physics. You don't need to go that far for that. Basically, I showed that picture where the state wanders into bigger macro state. The thing is that the bigger macro state is exponentially bigger. Let's say 10 to the 10 times bigger. So the Poincaré recurrence time for a system as small as 10 particles in a box are longer than the age of the universe. So it just never happens in practice. So the long time limit is not really a mathematical statement here. It's more like if you take some very long time, which is random, you will see the entropy is not down. It might be down sometime in future, but it just never happens because you will need to wait a really long time.
Nice. Okay, so maybe we can have two more questions. So there's an anonymous attendee. Is there a corresponding third law of thermodynamics for observational entropy, or is it still going to be the same?
Well, in my understanding, the third law is not really law, more like a convention. You just say, well, the entropy at temperature 0 is just 0. But that's really a convention because experimentally you cannot measure the observable entropy. We only measure differences in entropies. Because you always say, okay, entropy increased by logarithm of 2 if the system doubled. And that's all we see. Even in Clausius entropy is defined like ds equals dq over t. it's always the change. So the absolute value, it doesn't really matter. It's a convention. You can redefine the third thermodynamic law to be some some other number at t equals 0.
Okay. Yes, I think that's a. Okay, so we have one more question, maybe for last one. So that's from Junius Balista. Does your result depend on the model of the universe?
Well, it depends what you include, right? So so the key thing here is what you need for this to calculate this observation entropy is the definition of your phase space or Hilbert space. So that's one thing. So if you have, let's say, Hilbert space that includes tachyons or doesn't include tachyons, those are different Hilbert spaces. One is simply going to be bigger and it will give you a larger observation entropy. So first you need to decide which things you consider as real, and part of it, I guess, dark matter would be part of it. Maybe dark energy, but I don't know what are the states of dark energy. So that's one thing. And the second thing is that you need to pick your coarse gaining. And then I'm saying, well, probably if you want to compute the meaningful entropy, your coarse gain should be basically you put some local boxes around everything that seems to be in local equilibrium, and you coarse gain in energy and particle position. But in principle, you can choose any other coarse gaining, and the entropy will still increase. It's just that in that case, you cannot really interpret that entropy as thermodynamic entropy, but it will still increase.
Okay, so I think that's it for the question and answer portions. But if you have more questions, feel free to direct them to Dominik. I think he kindly gave us his email.
Happy to. Yeah.
Awesome. So I think now it's time for the presentation of the certificate of appreciation or recognition. Yeah. So here I read. So the Samahang, Pisika ng Pilipinas, Physics Society of the Philippines, in partnership with the National Academy of Science and Technology, presents this certificate of recognition to Dr. Dominik Šafránek for sharing his expertise as plenary speaker on the topic which entropy increases in isolated quantum systems during the 39th Samahang Pisika ng Pilipinas Physics Conference and annual meeting with the theme Accelerating National Progress via Physics from Quantum to Stellar and Beyond, held online from the 20th to 22nd of October 2021. Given this 22nd day of October 2021, signed by SVP President Dr. Ed Kwan Singh and SVP Secretary General Dr. Cyril Salang. So Dominik, thank you again for your wonderful contribution, and yeah, we learned a lot.
Thank you.
Thanks.
Thank you very much. It was my pleasure.